Hello and welcome to a lesson on the integration of polynomial functions. This lesson assumes you've already studied the lesson on differentiation of polynomial functions. We'll begin by defining integration as the reverse of differentiation, and we look at indefinite integrals leading up to a typical exam question. In the second part of the lesson, we'll consider definite integration, using as an example the area under a curve. To begin then, first consider integration as the reverse of differentiation. If we have a curve y equals x cubed plus 2x squared plus 3x plus 4, then dy by dx is 3x squared plus 4x plus 3. Now what if we define the integral to be going back from here to the original curve? So the integral of 3x squared plus 4x plus 3, and we write it as this sort of S sign in front of 3x squared plus 4x plus 3 dx, and the dx simply means we're integrating with respect to the variable x. Then the answer should be what we started with. So it should be x cubed plus 2x squared plus 3x plus 4. But I haven't got plus 4. The problem is, when dy by dx is equal to this, I have no way of knowing what the original constant was. And so all we can do is put plus c. It may have been the original function x cubed plus 2x squared plus 3x plus 4, but equally well, the term on the end could have been plus 5 or plus 6. And so the best we can do at this stage is to put plus c, and we call that the constant of integration. So here we have the general rule for polynomial integration. If we integrate ax to the power n, where a is a constant, we get ax to the power n plus 1, so we raise the power by 1, divided by the new power, divided by the n plus 1. We also got plus c, the constant of integration, because we can never be sure what the constant was originally. Points to note. This rule is fine for when we're talking about integrating x squared or x cubed and so on, but down at the lower powers, it's best to have a feel for what the answer is without using this rule. So for instance, if we integrate 3 with respect to x, we get 3x. Imagine if you had the line y equals 3x. If you differentiated, found the gradient, it would be 3. So it's natural that when we integrate 3, we get 3x, plus the constant of integration. Or more generally, if we integrate k, where k is any number, then we get kx, again plus the constant of integration. And in particular, if we integrate 0, then we get a constant. Think of the line y equals 5, a horizontal line, gradient is 0. Think of the line y equals minus 2, a horizontal line, if you differentiate, dy by dx is 0. So it stands to reason again that if we integrate 0, we must get a constant. Let's have a look and see if this rule here fits what we started with. If we integrate 3x squared, we raise the power by 1, we get 3x cubed divided by the new power. 3x cubed divided by 3 is x cubed. If we integrate 4x, well, we can think of x as x to the 1. We raise the power, we get x squared. So that's 4x squared divided by the new power, the 2, and 4 divided by 2 gives me 2, 2x squared. As we've just discussed, when we integrate 3, we get 3x. And we also get the constant of integration. We can't know that it's a 4. Okay, let's move on and look at some examples now. Let's work through these. Integrate first of all x squared with respect to x, and what we get is this is equal to x cubed, raise the power by 1, divide by the new power, plus a constant of integration. Integrate x to the power 7 with respect to x. Raise the power by 1, we get x to the 8, divided by the new power, plus a constant. Integrate 5x to the power 4 with respect to x, and we get 5 x to the power 1 more than 4 is 5, divide by the new power plus a constant. Now this one we can tidy up a little. 5 divided by 5 is 1, so this just becomes x to the power 5 plus a constant. Example 4. Integrate minus 3x to the power 5 with respect to x. Well, that gives us minus 3x to the power 6, 1 more than 5, divided by the new power, plus a constant. And we can cancel that 3 over 6 into a half, so that will be minus 1/2 x to the power 6 plus c. Integrate 7 with respect to x. Well, this is one of the special cases we were talking about earlier. If we integrate a constant, we just get that many x plus a constant. Check that. If you differentiate 7x, you would get 7. If you differentiate the c, a constant, you get 0. So 7 is the differential of this here, and therefore this is the integral of 7. And finally, integrate 0, and we just get a constant. 4 more examples now, but we're collecting terms together to make polynomial functions here. Integrate 5x squared minus 6x plus 4 with respect to x. That gives us 5x cubed, raising the power by 1, divided by the new power, minus 6x squared, divided by the new power, plus, if we integrate 4, we get 4x. And don't forget the constant of integration. Now we could just tidy this little term here. 6 divided by 2 is 3, so I'll write it once more. We get 5x cubed over 3 minus 3x squared plus 4x plus c. Number 8. Integrate 4x to the power 5 minus x squared plus 1. This will give us 4x to the power 6 divided by 6 minus x cubed divided by 3. If I integrate plus 1, I get plus x. And then there's the constant of integration as always. Simplifying this first term, we will get 4 sixths cancels to 2 thirds, so we get 2x to the power 6 over 3 minus x cubed over 3 plus x plus c. Integrate x to the 4 minus x cubed plus x squared minus x plus 1 with respect to x. Working along the line, we get x to the 5 over 5 minus x to the 4 over 4 plus x cubed over 3, just raising the powers by 1 and dividing by the new powers. Integrate minus x, I get minus x squared over 2. Integrate plus 1, and I simply get plus x, and then there's the plus c on the end. Last example with some fractional coefficients. Integrate 2 thirds x squared plus a quarter x minus a half with respect to x. And that gives us 2 thirds multiplied by x cubed divided by the new power plus 1 quarter multiplied by x squared divided by the new power minus, if I integrate minus a half, I get minus a half x plus a constant. So let's tidy this up, and we've got 3 times 3 in the denominator, so that's 2x cubed over 9 plus x squared over 8 minus x over 2 plus a constant. And that completes these set examples on what we call indefinite integration. Indefinite because we've got a constant in it that we can't get rid of each time. The first part of this lesson has been on indefinite integration, where constants of integration are involved. And to round it off, we'll look at a typical exam question. The gradient function of a curve is given by dy by dx equals 3x squared plus 4x minus 5. The curve passes through 3, 4. Find the equation of the curve. Well, we start with the indefinite integration. Let me write down dy by dx. Dy by dx is equal to 3x squared plus 4x minus 5. And from that we can infer that y must be of the form integrate term by term. We get 3x cubed divided by the new power 3 plus 4x squared divided by 2 minus 5x plus the constant of integration. So y is equal to x cubed, because the 3's cancel, plus 2x squared minus 5x plus c. But that doesn't just define one curve, it defines a whole family of curves for the various values of c. So the exam question gives us a point on the curve, 3, 4. And by substituting those values into the equation of the curve, we can find out what the constant c must be. So let's say substitute the point 3, 4. So we get 4 for the y coordinate is equal to 3 cubed plus 2 times 3 squared minus 5 times 3 plus a constant. So 4 is equal to 3 cubed is 27 plus 3 squared is 9. 9 times 2 is 18. And minus 5 times 3 is minus 15 plus c. So that gives us 4 minus 27 minus 18 plus 15 equals c, just taking all the other terms to the left hand side. So what have we got? We've got 27, 37, 45 negatives there, plus 15 makes it 30 negatives, and then plus 4 makes it minus 26. So minus 26 is equal to c. Therefore we have our final answer. The equation of the curve is y equals x cubed plus 2x squared minus 5x, and we can now replace the plus c with minus 26. And that completes this question. Now for the second part of the lesson, we're going to look at definite integration. And I'm going to introduce this by looking at the area under a curve. So let's suppose I've got this curve here, and we're going to declare the area to be A, measured from some arbitrary point, some unknown point, all the way along the curve to the point where the x coordinate is x. So we call the general point on the curve xy. Now what would happen if we allow x to go a little bit further? So we increase it by a small amount delta x. Well, that would also cause a small change in y, let's say an increase of delta y. And we'd get a little bit more area. We'd get the area under this blue line between these two vertical red lines added on to the original area. And I'm calling that delta A, a small bit of area. So let's see if I can write down some kind of relationship for delta A. I can say that delta A, well, it's bigger than this small rectangle here. So it's bigger than the y coordinate y multiplied by delta x. So let's say delta A is greater than or equal to y times delta x. But this area is less than the area of this large rectangle here. Now this is delta x wide, but the height is now the y coordinate of this point, which is y plus delta y. So delta A is less than or equal to y plus delta y multiplied by delta x. I'm now going to divide this inequality through by delta x. So on the left hand side, y delta x divided by delta x is just y. That's less than or equal to delta a divided by delta x. And that's less than or equal to y plus delta y times delta x divided by delta x is just y plus delta y. And now I'm going to let delta x tend to 0, that's the kind of thing we do in calculus. Let the change get smaller and smaller till there's no change at all. So as delta x tends to 0, so will delta y, because we'll get closer to this point. And so will delta a for that matter. So as we let delta x tend to 0, instead of having delta a by delta x, we'll have what we call dA by dx, the differential of a. And you'll see that when delta y tends to 0, then this is greater than or equal to y, but it's also less than or equal to y. And so it must be equal to y. So we end up with dA by dx is equal to y. Now I can find a if I know dA by dx. The area A will be the integral of dA by dx, so it's the integral of y, but with respect to x. So we need to express y in terms of x. Now that will give me the area up to any particular point, so I could evaluate it, let's say, when x is 2, and I get the area from some arbitrary point over here on the left up to x is 2. I could evaluate at x is 3, and I get, again, the area measured from some arbitrary point on the left up to x is 3. Well, this arbitrary point comes from the plus c, the constant of integration. But if I subtract one from the other, let's say I subtract the area measured up to x equals 2 away from the area measured up to x equals 3, then what I will get is the area under the curve between x is 2 and x is 3. And that's what we're going to do now. Example 1. Find the area between the curve y equals x squared, the x-axis, and the lines x equals 2 and x equals 5. So I'm looking for this area here. And we use this formula that the area is equal to the integral of y dx, y with respect to x. But we put limits on it. We integrate it from 2 to 5, between x is 2 and x is 5. And I can rewrite this as the integral from 2 to 5. I'm going to express y in terms of x. Well, y is x squared. So it's simply the integral of the curve function expressed in terms of x. And what we do now for notation is we use a square bracket when we integrate. And we keep the limits on between 5 and 2. When I integrate x squared, I get x cubed over 3. Plus a constant, you may think. Well, we don't normally put the constant in because we're going to subtract one integral from another. The plus c's would cancel out, so there's no point in putting them in. It wouldn't affect the answer if you did. So this is evaluated at x is 5, and we get 5 cubed over 3. Evaluated when x is 2, and we get 2 cubed over 3. And by subtracting those, we get the area in between them. Because evaluating it at 5 gets the area from some unknown point on the left up to 5. Evaluating it at 2 gets the area from that same unknown point up to 2. So the difference between them is the area I'm interested in. So what does this give me? 5 cubed is 125, so that's 125 over 3. Minus 2 cubed is 8, so it's minus 8 over 3. 125 minus 8 is 117. And 3 goes into 117 exactly. 3 goes into 11 3 times, 2 left over, 3 into 27, 9. So it's 39 units squared. Whatever units we've set the graph up in, maybe it's in centimeters or meters, whatever. So the area under the graph between 2 and 5 and above the x-axis is 39 units squared. Now a second example of finding the area between a curve and the x-axis. I have here a graph of y equals x multiplied by x minus 2 multiplied by x minus 4. So this graph cuts the x-axis at x is 0, x is 2 and x is 4. And here I've multiplied out the function to give y equals x cubed minus 6x squared plus 8x. Find the area between the curve and the x-axis between x is 2 and x is 4. So we're trying to find this area I've marked A. So the area is given by the integral of y with respect to x. And I'll just write straight away that y is x cubed minus 6x squared plus 8x. So it's the integral of that with respect to x. And it's between the limits of 4 and 2. Square box for when we integrate. X cubed integrated is x to the power 4 over 4. And then we've got minus 6x cubed divided by the new power 3 plus 8x squared divided by 2. And again, we don't bother with the constant of integration because it would be subtracted from itself. And that's between 4 and 2. Let's simplify two of these terms. We've got x to the 4 over 4. This one simplifies to minus 2x cubed. And this one simplifies to plus 4x squared. And that gives us a bracket minus a bracket. The first bracket, I'm putting x is 4 in here, so we get 4 to the power 4 over 4 minus 2 times 4 cubed plus 4 times 4 squared. And we're going to subtract from that the bracket evaluated with 2 in for x. So we get 2 to the power 4 over 4 minus 2 times 2 cubed plus 4 times 2 squared. Right, the first bracket. 4 to the power 4 divided by 4 is 4 cubed. 4 cubed is 64. 4 cubed is 64 minus 2 times 64 is minus 128. And 4 squared times 4 is plus 4 cubed, which is plus 64. Minus the second bracket, 2 to the power 4 is 16, divided by 4 is 4. 2 cubed is 8, times minus 2 is minus 16. And 2 squared is 4, times plus 4 is plus 16. And this first bracket, plus 128 minus 128 is 0. And this second bracket, we've got 4 minus 16 plus 16, which is just 4. There's a minus sign at the front, so it's minus 4. So the answer is minus 4. Now what is the significance of the minus sign? Well, the minus sign simply indicates that the area this time is below the x-axis rather than above. So we can say that the area is equal to 4 units squared. And that will be the case whenever you've got a minus sign, the area is underneath the x-axis. But we do have to be careful, because if we were integrating from there to there, from 0 to 4, you wouldn't get the total area enclosed between the curve and the x-axis. That would be a positive area, that would be a negative area. and they would net off against each other. So if we wanted that total area, the only way to do it would be to find the integral from 0 to 2, find out what that is, find the integral from 0 to 4, which we've just done, ignore the minus sign, and add it to whatever we got for that area there. Right, that brings us to the end of this lesson on the integration of polynomial functions. You'll now find an exercise covering all the types of example we've been working on.